Okay, well, I think we should start going then. So welcome back to day 2 of this GMT Short course. You know what the deal is going to be now. It's going to be very similar to yesterday. We'll have me saying a few things right now, and I don't need 10 minutes, so we'll save some of that for Dong Dong, who's going to go over the seismology aspect of this project and of this course. And that's going to take us through the first 90 minutes. And then we'll have the usual 1-hour break for breakfast, lunch, tea, bedtime, whatever you do there. And then I think, because Dong Dong's giving this from China, he will be in bed after that break. So the rest of us will try to handle any questions that might come up during the seismology section. And if we are incapable of doing this, which could happen, then I'm sure Dong Dong will clean up tomorrow morning any remaining questions that we could handle. And then we're going to switch gear and talk more about geodesy related plotting that Eric Zhu is going to do for us. And that's going to be sort of the bulk of the start of the second half, if you will, although they're not equal halves. And then after the break, we'll do some animation with GMT that I'm going to do. And that's going to be the end of day 2. So after we have these first 2 days, the third day tomorrow, we will start talking about and working on the class projects, the individual project that you have to complete and submit to get credit for having taken the course. So we'll talk more about that tomorrow morning. But I hope everybody have a good time so far. Everything is running relatively smoothly. Again, if there's some specific complicated issue that we aren't able to show on Slack, solve on Slack, please post a GitHub issue on GMT for Geodesy GitHub page, so we can sort of track and work with you maybe offline on any problems. Okay, so with that, I think I'll save 5 minutes extra for Dong Dong and let him take it away. Dong Dong. And I'll stop.
Hi, yeah, hi, I'm Dong Dong. Because it's in China, and so it's close to 11 p.m. And because I have very unstable network while share screen, so I record a video 1 or 2 days ago, and I will let Melissa play this video. And okay, Melissa, can you play this video?
Let me share the screen here. Let me find
it.
Sorry.
Yeah, thank you.
I will admit people will come late, Melissa. You can just do the video.
Okay, thanks. All right, do you see the black screen?
Yeah.
All right.
Hi, good morning, good afternoon, and good evening. I'm Dong Dong Tian from China University of Geosciences. The topic of this session is GMT for seismology. So let's first go into the seismology folder. Seismologists use seismic waveforms to study how earthquake happens, how seismic waves propagate through the earth, and also seismic structure inside the earth. The seismology community actually use GMT a lot. We use GMT, the plot module, to plot lines and symbols, the coast module to plot the coastlines, and the grid image module to plot topography relays. In addition to these core modules, GMT also provides 4 modules that are highly related to seismology research. Here is a summary figure for the 4 modules. The first module is called MECA. MECA can be used to plot focal mechanisms of earthquakes on a 2D map. And the COPE module can be used to plot focal mechanisms on a cross-section. So like if the cross-section is vertical, then the y-axis is the depth. The POLO module can be used to plot the first motion priority of the observations. And the seismologists use these observations, then can determine the focal mechanisms of the earthquake. The second module can be used to plot seismic waveforms with wiggles in deck format. Because this is a workshop for geology, so we will only focus on the first two modules, Mecha and Curve. In this session, I will show you how to use Mecha and Curve to plot focal mechanisms or beach balls on a 2D map or a cross-section view. Before we start, actually, we have to have a very basic understanding of focal mechanism and the beach balls. Here is a video made by Iris. This short video actually gives a very good introduction to focal mechanisms and the beach balls. I don't think I can explain them better than this video. So let's just watch this video first to make sure that you understand focal mechanisms and the beach balls before we start to learn the Mecha and Curve modules.
When an earthquake occurs, seismologists create graphics of focal mechanisms, informally referred to as beacons, to show the faulting motions that produce the earthquake. The focal mechanisms are based on the direction of the first arriving P wave. Let's investigate the patterns of P wave arrivals that result from different faulting mechanisms by first considering a Spreadstone earthquake. When an earthquake occurs, seismic waves radiate away from the epicenter in all directions. The parallel green lines in the northwest and southeast quadrants have been compressed during the earthquake, and the northeast and southwest quadrants were stretched. Let's look at the P waves moving away from the epicenter. We will insert slinkies to demonstrate and exaggerate the compression and dilatation features. Northwest and southeast of the epicenter, the rock is compressed, and the first arriving P waves at those stations are pushed away from the epicenter. Northeast and southwest of the epicenter, the rock is stretched, and the first P waves are pulled toward the epicenter. The dilatational and compressional arrivals are often shown as plus and minus signs, respectively. With observations from many stations, we see two quadrants of compressional arrivals and two quadrants of dilatational arrivals, separated by perpendicular nodal planes. To simplify the illustration, compressional quadrants can be shaded, and dilatational quadrants are left unshaded, producing a P wave first motion pattern that looks like a beach ball. Notice that this pattern of dilatations and compressions can be produced either by right lateral strike slip faulting on a north-south fault plane or left lateral strike slip faulting on an east-west fault plane. Therefore, you must use geological knowledge of the region to decide which nodal plane is the fault plane. For example, if an earthquake with an epicenter on the San Andreas fault had a focal mechanism that looked like this, the most likely choice would be that the fault plane is oriented northwest to southeast, parallel to the stripe of the fault we observe at the surface. Now let's consider a right lateral strike slip earthquake on the Kane fracture zone in the Atlantic. This earthquake will produce compression in the northeast and southwest quadrants and dilatation in the northwest and southeast quadrants. Since there are no nearby seismometers, the P wave first arrival patterns are observed at distant stations. Seismic energy travels away from the earthquake in all directions, so we need to consider the three-dimensional geometry of the ray paths. To do this, it is convenient to imagine a sphere, called the focal sphere, surrounding the earthquake hypocenter. Rays that travel to distant stations will radiate from the earthquake to the lower hemisphere of the focal sphere. To keep things simple, let's look at two cross-sections at more or less right angles. First, make a vertical cut into the earth through the hypocenter in a northeast-southwest orientation. P waves leaving the earthquake and traveling to Lima, Peru in the southwest quadrant, or to Madrid, Spain in the northeast quadrant, will have compressional first arriving P waves that push up away from the earthquake and are observed as an initial upward vertical motion on the seismograms. The second cross-section will show P waves traveling to Detroit and Seattle in the northwest quadrant and to Cape Town, South Africa in the southeast quadrant. These will have dilatational first rising P waves that are pulled toward the earthquake, observed as a downward earth motion on their seismographs. By examining first arriving P waves at many stations over a range of azimuths and distances from the earthquake, we can determine the pattern of compressions and dilatations on the lower hemisphere of the focal sphere. As we have seen, a strike slip earthquake produces a crossing pattern of approximately vertical faults, or nodal planes that separate two compressional and two dilatational quadrants. Now let's look at the pattern of compressions and dilatations that result from an earthquake on a normal fault, like on the east side of Steens Mountains in the Basin and Range province. The block on the east side of this fault has dropped down with respect to the block on the west. Viewed in cross-section, we see that compressional first arriving P waves will radiate to the east and west from the hypocenter at shallow and intermediate downward angles. Dilatational first arriving P waves leave the hypocenter at a steep downward angle. The resulting focal mechanism has perpendicular nodal planes that cut the lower hemisphere of the focal sphere in an orange slice appearance with compressions on the outside and dilatations in the center. This is the focal mechanism signature of an earthquake on a normal fault produced by extensional forces. Because of the way the fault plane intersects the bottom of the focal sphere, the boundary between the regions on the focal mechanism is curved. Finally, let's consider a thrust fault, like that beneath Sierra Y de Paulo, within Sierras Pampeanas of northwest Argentina. This is a west vergent thrust fault, wherein the block on the east moves up and over the block on the west. Viewed in cross-section, we will see that dilatational first arriving P waves radiate to the east and west from the hypocenter at shallow and intermediate downward angles, whereas the compressional first arriving P waves leave the hypocenter at steep downward angles. The resulting focal mechanism has perpendicular nodal planes with the same orange slice appearance observed for a normal fault. However, for a thrust fault earthquake, dilatations are on the outside and compressions are in the center. This cat's eye focal mechanism is the signature of an earthquake on a thrust fault produced by compressional tectonic forces.
Okay, let's go back to this GitHub page. Here are three main types of faults: strike slip fault, normal fault, and the reverse fault. As you can see, earthquakes happening on these different types of faults have very different focal mechanisms, and their pitch faults are also very different. So from pitch faults, we can then know the orientation of the fault and also the slip direction of the fault. After the brief introduction to focal mechanisms and the pitch faults, now it's time for us to learn how to use Mecha and COPE. To use these two modules, we first need some example data. Here are the example data we are going to use in the following tutorial. This data has 3 lines. Each line represents a focal mechanism of one earthquake. The data has 8 columns. The first 3 columns are the location of the earthquake, longitude, latitude, and depth. The next 3 columns are the focal mechanism information. In this conversion, we use the strike, slip, and rake to describe the focal mechanism. These 3 parameters are all angles in degrees. And the next column is the magnitude of the earthquake, just how large the earthquake is. And the last column is the title of the event. It's just a string to describe what the earthquake is. Now let's copy the example data and save it to a new text file. We will use this file in our following scripts. So let's copy these 3 lines and open VS Code. Let's create a new file and save it here. And let's save it. We can call it mecha.dat. We also need to create a new file for our bash script, and let's save it. Call it beachball.sh. Like any GMT commands, GMT bash script, this script should start with GMT begin, and then we also need to give the name of the image. So let's call it beachballs, and it should end with GMT and should. In this part, we are going to use the mecha module to plot beach balls on 2D maps. So let's type GMT mecha. And we need to pass the example data to this module. So let's type mecha.dat. Let's save it and run the script to see what happens. Bash beachball.sh. You don't see any figure, and you will see an error in your terminal. The error says that you must specify the -s option. So what's the meaning of the -s option? I don't know. I don't remember. So I need to read the official documentation of the mecha module. So in the terminal, I can type gmt docs mecha. This command will open the documentation for the mecha module. Let's type enter. And this is the documentation for the mecha module. You can see that there are many options here. And here is the -s option. Let's click this link. You can see that the -s option actually selects the meaning of the columns in the data file. It means that we need to tell mecha what's the data format for the input data. That's because focal mechanisms can be specified in many different ways. We already called it conventions. So focal mechanisms, there are many conventions to specify focal mechanisms. So like GMT actually supports many different conventions: -SA, -SC, -SM, SD, SD, or -SP. There are many. And let's look at -SA. -SA means that the focal mechanisms are specified in Archie and Richard convention. So in this convention, the first 3 columns are the longitude, latitude, and the depth of the earthquake. And the next 3 columns are the strike deep rate of the fault movement. They are all in degrees. And the next column is the magnitude, how large the earthquake is. And -SC means that focal mechanisms are given in global CMT convention. In this convention, we need to provide the strike deep rate of the first nodal plane, and we also need to provide the strike deep rate of the second nodal plane. Another very commonly used convention is called seismic moment tensor. It's also a very general way to specify focal mechanisms. A seismic moment tensor is just a 3x3 tensor. It's similar, or it's the same as, it's very similar to the stress tensor or the strain tensor. It's by 3x3, so there are 9 components. But because the moment tensor is symmetric, there are only 6 independent components. In this convention, we need to provide the longitude, latitude, and depth of the earthquake. After that, we need to provide the 6 components: MRR, MTT, MFF, MRT, MRS, and the MTF of the tensor. So in this session, our example data actually follow the Archie and Richard convention. So we will use -SK here. So after telling that mecha, we are using the Archie and Richard convention. We also need to specify the size of the beach ball. So let's use 1 centimeter. So let's run the script again. beach ball dot sh. You should see a figure like this one. So there are 3 beach balls here, but they are clipped. That's because we are plotting beach balls on maps, but we don't give the region projection and the frame settings for this figure. So let's go back to the script. And before the GMT make command, let's plot the base map. So GMT base map. And minus here, because this is a geographic map, so we need to geographic projection like title projection, and the size of the image is 10 centimeter, and we want to have an automatic frame, so minus B A F. And we also need to give the region of the study of the region of the map. So minus R. If we go back to the example data, we can see the locations of the earthquakes, the longitude and the latitude of the earthquake. So based on this information, we can set the study region to 110 and 120, and the longitude is 30 to 35. So let's save it and run the script. Okay, now you should see a figure like this one. Using this simple makeup command and the minus S option, we can now plot beach balls on maps. By default, all the beach balls are plotted at the locations of the earthquake. The compressional part are black, and the extensional part are white. The title of the events are plotted above the beach balls. We can change all of them. If you look at the beach balls carefully, you will see that the beach ball size are different. That's because the 1 centimeter here is the beach ball size for a magnitude of 5 earthquake. The real beach ball size is proportional to the magnitude. So for example, for this strike slip event, its magnitude is 4. So the beach ball size is a little smaller. And for this normal fault earthquake, its magnitude is 6. So its beach ball size is larger. If you want to plot all the beach balls using the same size, you can simply append plus M to the minus S option. Let's see what happens. So you can see that now all the beach balls have the same size. Okay, I will remove plus M and then go back to the original example and then run it again. So we can also change the properties of the titles. We can change its angle, we can change the font, the size, and also the position. This can be done by appending more modifiers to the plus minus S option. So we can use plus A to change the angle of the titles. A means angle, and we can use plus A30, which means rotate the titles by 30 degrees. So this is the new title, and we can also change the font by using plus F. F means font, and we want a small size, so we can use 6-point size for the text. And I want a blue title, so I use blue, and let's run the script. So the title now is smaller and has a blue color. We can use plus here to put the title at other locations. By default, it's above the beach ball, so it's top and top center, TC. And I want to put the titles below the beach ball, so I can use bottom center instead. So now the title are at the bottom of the beach balls. I can also add some more offsets to the titles by using plus O And I will give 0.2 of that in x direction, and also the centimeter in the y direction. And this is the final data. Sometimes
Melissa, I think your sound has to be on for us to be able to hear.
the 0 point.
Oh.
And so we can change.
Could you please rewind just 30 seconds so we can catch that part?
Here. We'll remove plus m and then go back to the original example and then run it again. So we can also change the properties of the titles. We can change the angle, we can change the font, the size, and also the position. This can be done by adding more modifiers to the plus minus s option. So we can use plus a to change the angle of the titles. A means angle, and we can use plus a 30, which means rotate the titles by 30 degrees. So this is the new title, and we can also change the font by using plus s. S means font, and we want to a small size, so we can use 6-point size for the text. And I want a blue title, so I use blue, and let's run the script. So the title now is smaller than the blue color. We can use plus here to put the title at other locations. By default, it's above the pitch ball, so it's top and top center, TC. And I want to put the titles below the pitch ball, so I can use bottom center instead. So now the title are at the bottom of the pitch balls. I can also add some more offsets to the titles by using plus O, and I will give 0.2 of that in x direction, and also the centimeter in the y direction. And this is the final data. Sometimes you probably do not want to see the titles because maybe you have too many aspects and too many beach balls. If there are so many titles, then the figure will be very messy. So it's very simple. You can simply change the font size to 0 point. And so we can change the 6 point to 0 point. Then the title will disappear. Okay, so the title just disappear. Okay, so these are the modifiers that can be used to control the appearance of the titles. Okay, I will remove this following and go back to the initial original example. Because most earthquakes happen along a fault, so usually you will have many earthquakes in a small regions, and they may overlap each other. In this case, you may want to offset your pitch balls to another place so that you can still see the location of the pitch ball or locations of the earthquakes, and also can see their focal mechanisms. This can be done by adding 2 more columns to your input data. So let's go back to our example data, mac.dat. We can add the location, new location for the pitch balls before the title of the event. For example, for this strike slip event, the location of the earthquake is here, and now I want to plot the pitch ball here. Now I want to plot the pitch ball here. So the location of this point is 1, 1, 1, and 31. So this is the location of the pitch ball. And for other events, I don't want to have any offsets for them, so I can simply use 0 and 0 for the reverse spot. and 0, 0 for the normal fault. Here, 0, 0 means that no offset for these beach balls. So let's run the script again. Bash beachball.sh. Nothing happens. The strike slip. There are no offset for the strike slip events. That's because we still need to provide the -A option to make the offset happen. So let's run the script again. So you will see that this is the location of the earthquake. This is the location of the earthquake, and now the beach point is offset to a new location here. And let's go back to the example data. We can also change the reverse fault. Let's say I want to plot the beach ball here. So here, so the new location should be 114 and 34. And for this number 4, I want to plot it here. Then the location is 117 and 31. Okay, let's save this example data and run the script again. Bash beachball.sh. You will see that all the earthquakes are offset into different locations. So this line connecting the original location of the earthquake and the new location of the beach balls, we can change the pen of this line by using +pen and +P, and we can use set a pen thickness to 0.5 point and use red color. Okay, let's see what happens. Okay, so you can see that. Okay, I will use a thicker line, 1 point. Okay, you can see the line is much thicker now, and it's also possible to plot a circle here at the original location of the earthquake. This can be done by adding +S, and I want to have a circle with a size of 0.4 centimeter. Let's see what happens. Okay, now the circle is too large. Okay, I will change it to 0.2 maybe. Okay, so this is the final figure. And now from this figure, we know the location of the earthquake, and we also can easily see the focal magnetism of the earthquakes. Okay, as I will remove the -A option here and still go back to the original example, and let's run the script again. By default, the compressional part are black and the extensional part are white. We can change the color of these two bars by using -G and -E. The -G controls the color of the compressional part. We can use a color like red, and so we have a red beach ball, and we can also use a -E, which controls the color of the extensional part. I can use another color like light blue. Okay, so we can use -G and -E to change the color of the extensional and the compressional parts. Okay, now let's remove the -G and the -E option and go back to the original example. Let's run the script again. So this is the original image. From the survey image, we can know the locations of the earthquakes. We can know the focal magnetism of the earthquakes based on the beach balls. We can also know their magnitude based on the size of the beach balls. But what's still missing is the depth information of these earthquakes. So how can we also show depth information of these earthquakes on this map? This is usually done by painting the compressional part by different colors. and the color is determined by the depth of earthquake. In the Mecha module, this can be done by using the -C option. The -C option means that we need to provide a CPT file which maps the depth of the earthquake to a color, and then Mecha will use the color to paint the compressional part. So using -C here means that we need to provide a CPT first. So before running the GMT Mecha command, we need to make a CPT file. So we can run GMT make CPT, and then we need to choose a master CPT. There are many CPTs in GMT, and I will choose -C and use the size CPT. We also need to give the minimum and the maximum value in this file using -T. Let's go back to our original example data. So the third column is the depth of the earthquakes. So these three earthquakes have a depth of 15, 25, and 45. So the minimum, we can give a minimum value of 0, and we can set a maximum value, maximum depth to 50. I think these two values make sense. So we can use -T, 0, and the maximum is 50. So let's run the script again. Now we can see that the three beach balls have very different colors for the compressional parts. We also need to add a color bar so we can know what the color means. So GMT color bar and -B, yeah. Okay, so this is a color bar of the beach ball color, beach ball depth, and I also want to have a label, so I can add a label like depth kilometer, and I want to put the color bar at the right of the map, so I can use -D and Gmt Jrd put the color bar at the middle right of the map. So this is our final figure. So from this figure, it's clearly we can see that the reverse fault has a very shallow depth, and the strike slip has a medium depth, maybe 25 kilometers, and the normal fault earthquake have a very large earthquake, larger than 50 kilometers. Okay, so that's all about the Mecha modules. In this part, I introduced the -S, -C, -G, -E, and also the -A option to control the locations, the title, and the color of the compressional part and the extensional part of the beach balls. So that's all about the Mecha module. Next, let's go to the Cope module. The Cope module is used to plot beach balls on cross sections. Usually we use vertical cross section, so the y-axis is the depth. Let's first go to VS Code and create a new file for the following examples, and let's save it to cross section.sh. So we still need to use GMT begin and cross section GMT and show, and we are going to use the Cope module. And the Mecha module and the Cope module, they have the same input. So we need to pass the example data mecha.dat to this module. And then I will go to the terminal and type gmt docs-cope to see the documentation of this module. As you can see, there are many options here, and most of the options actually have the same meaning in Mecha. So the -S option can determine the column, the meaning of the columns in the input data, and the -C option can determine the color of the compressional part based on the earthquake depth, and the -E and the -G option to determine, to control the colors of the extensional part and the compressional part. So they are all the same. So in GMT code, we also need to use -S option, -SA 1 centimeter to tell that our data is in Arc and Richard convection, and the size of the beach ball is 1 centimeter. The most important and the unique option in code is -A. -A is used to select the cross section. Is used to specify the cross section. There are many different ways to specify the cross section. So -A, capital A, small a. In this way, we can give the locations of the starting point and the ending point of the cross section. And if we use -AB, we can give the starting point, the location of the starting point of the cross section, and also the strike and the length of the cross section. Here we are going to use -A, capital A, small a here. And let's go back to this image. Assume that we are going to use to have a cross section like this line, and we want to plot all the beach balls along this cross section. And then the starting point of the cross section is 11033, and the end point of the cross section is 12033. So if we run this script, we will see an error. The error says that we must specify -R option for the study region, or the -A and the plus small r modifier. That's because in the cross-section view, the x-axis is the distance along this profile, and the y-axis is the depth. So we have to tell COPE that the study region and so now we can use +R to let COPE to automatically determine the region of the map. And let's run it again. Now we can see a bit like this. Here we also need want to give the projection information and also automatic frames. And so let's use -J, and we know that it's a linear projection. The x direction is the distance, so we can have a 10 centimeter width, and the y-axis is the depth. I can give 5 centimeter, and we want to have automatic annotations and the frame. Let's run the script again. Okay. Now we have three. We already have the 3 beach balls on the cross section. As I mentioned before, this is the distance along the profile. So 0 kilometer is here, and the maybe 900 kilometer is here. And okay, I can change a little about the labels. So for the x-axis, I can add a label called distance kilometer. For y-axis, we can add a label called depth kilometer. And let's run the script. So for the y-axis, 0 is here, and this is 50 kilometer. Usually we want to reverse the y-axis so that this is the depth 0 and this is depth 50. This can be done by give a negative height to the map. So we can change 5 centimeter to -5 centimeter, and then we can run the script again. If you look at this figure, you probably are not satisfied with the automatic range for the y-axis. You probably want the y-axis to start with 0 and then you can remove +R, and we can manually specify the region. So -R, and the x-axis is from 0 to maybe we can use 10,000 kilometers, and the y-axis is 0 to I want to have 60 kilometers. So let's run the script. Okay, now it looks better. And as I mentioned before, we can use the -E option, and also like -C option to control the colors. Like we can use -G and to have a red color, and the -E to have a light blue color for the compressional part and the extensional part. Okay, so all the other options are the same in COPE and the Mecha, so you can try yourself. Okay, that's all about the COPE module. After learning the Mecha and the COPE modules, now you can plot beach balls of real earthquakes. Many agencies like Global CMT projects and the USGS provide focal mechanism of earthquakes. So you can just download focal mechanism information from these agencies and then plot them using Mecha and COPE. Here, I will show you how to get focal mechanism information from the Global CMT project. Let's go to this GitHub page. This is a link for the main site of the Global CMT project. This project provides focal mechanism information of global earthquakes with magnitude greater than 5.5. So we can scroll down to this link, the CMT catalog web search. And now you can select the focal mechanism information based on the date, based on the magnitude and the locations. For example, let's set the starting time from 2010, the first day of 2010 to maybe the last day of 2015. And then we don't set any magnitude constraint. And for the locations, we can search the earthquakes around like Japan. And the latitude is about 30 degrees to maybe 50 degrees. And the longitude is from 125 to 150. And we can also limit the depth of the earthquakes. Then in the output type, we can select the GMT PS Mecha input and click the down button. Then you will see a list of earthquakes here. There are many earthquakes here. You should be careful that the columns of you should be careful about the meaning of the columns. The first 3 columns are the longitude, latitude, and depth of the earthquakes. And then there are 6 components of the seismic moment tensor. So the output of the global CMT catalog is given by seismic moment tensor. So when you use Mecha and COPE, we need to use -SM, -SZ, or -SD. So we can't use -SA because it's not Archimedes and Richard convection. It's given by seismic moment tensor. And then we just need to copy these lines and save it to a file. And then we can use this file to plot beach balls. We can pass this file to Mecha and COPE to plot beach balls of all these earthquakes. Okay, here is an example, and you can split into teams, and then you can work on together to determine that, to discuss what's the commands and options you are going to use to plot a figure, 2 figures like this one. So this is a map view, and using Mecha, and this is a cross-section view use COPE. And in this map view, we can use grid image to plot the Earth relief, and then Mecha and to plot all the focal mechanisms. And in this figure, the color of the compression part are color coded by the depth of the earthquakes, and for the cross section view is similar. I think that's all, and you can you can also try yourself to find the best solution to plot these two images. If you are if you need some inspirations, then you can see this script here. Okay, that's all about the GMT for seismology. Thank you.
All right, welcome back after the long break. So the next section is on geodesy, and we are lucky to have Eric Zhu here to show us how that is done. So Eric, you have I think you have a total of 90 minutes, including whatever time for breakouts and so on.
Oh, okay. So there's a link that hopefully you guys have received either from the email or in the Slack channel. They are the data to be used for this session. And for the sake of smooth and quiet demo, I recorded the video and we're going to play that. Otherwise, you might hear some unpleasant noise. So Melissa, could you please play the recorded video?
I didn't get a recording.
Oh, I'll send you the link. Copy link address. And I'm just going to send it to the chat.
Okay.
It's on YouTube, so.
There it is. Yeah, see it.
All right. Give me a second here.
Sure.
Can everybody see?
Yeah, I can see it.
Okay. Let me see if the sound's going to come through.
Hi, everyone. I'm Xiaohua Xu from UT Austin. Sorry that I have to make this lecture in this format. So we'll be going over the tools in GMT to plot geodetic data, mainly targeting plotting vectors. So there are many kinds of geodetic data, like grids or lines or vectors or like deformation field. And GMT has all the functions to plot them. But over here, we're going to go over some of the functions, mainly using the plot function in GMT and with this -SE option for vector attributes. So there are like a bunch of commands that you guys can go through probably, and we're going to do this hands-on mode. So let me stop share and switch to the VSC. Share screen. All right. So over here, what we're going to do is that we'll do a real demo to sort of go through all these vector attributes and sort of help you guys understand how you can control the plotting of vectors. So let's get started. We're going to do a GMT -- new script. We're going to do it in Bash. So let's call this plot vec sh. And now you see that, oh, I'm in the wrong directory. Let me move this to this directory, go to vectors. So there are like a bunch of files in this folder that's downloaded before this part starts. So that contains some of the example data set that we're going to use later on. But for the moment, let's open this plot web.sh. So now you can see that this is calling bash, and you want to specify a session name, just call it 11. And we want to call this figure name to be vec, and in the format of PNG. But before we really get started, we do want some data to be plotted, right? So we're going to create a data using the echo command. Say that we want to plot a vector that starts from 0, 0, with the value being 1 and 1. Because this is using the -SE option, so it's actually allowing to plot the uncertainty circle. So we're going to add some uncertainty to this arrow, that is 0.2, 0.2. And the last column in the input is actually the, how to say, the correlation between these errors. For the moment, let's just call it, we're going to use no correlation between them. So in the end, it's going to come out as a circle. If you give it some kind of a correlation, then it's going to become an eclipse. So let's type this data, redirect this data into a file called maybe temp.dat. Then we'll start plotting. So the command that we'll be using in GMT is called willow or PS willow, and using the -SE option. So there are 3 inputs associated with this -SE option. The first one is the scale you'll be plotting. So here we're going to just use full scale, like 100%, which is 1.0. And the second input is actually the confidence level. So here we're going to use 6.65, which corresponds to like 1 sigma. So that's basically when you give this number over here, if you use 1 uncertainty, it's going to show up as the exact value. And the last one is actually the font size. If there are any like label associated, we're just going to use default like 10 over here. And we also want to specify the some line parameters. We want to give the width of 1 pixel. And if we save this script, and then in the command window, let's call bash plot vec.sh. Oops. Some error.
Melissa, I think there are some windows that's getting into the way of the screen share. Is it possible that you drag these?
Because I didn't give it a projection. I forgot to give it a projection. So
yeah,
let's set a parameter called, let's say, JRB equal.
Here, let me pause it. And it's in the way.
Yeah, there are a couple of Zoom windows that's sort of blocking the screen share. They show up as like a couple of like boxes in the middle of the screen share.
I wonder if I make it this way. Do the screen shares go away if I share it this way?
Yeah, this is better, I think.
Okay. I'll play it this way.
Plus, let's use Cartesian coordinates. Say we're gonna give it a size of 3 and 3 because this is sort of wraps up this vector. And -r, let's start from -1 to 2, which matches the 3 sides. So everything is in scale, -1 and 2. And we're gonna give the frame annotation being 1, frame being 1, and G being 1, grid line being 1. And we're going to call that parameter right over here. Let's call it $JRD. If we save it, let's go one more time. Okay, it has shown up. 1 second. Let me open this. Okay, double column, close this. So now you see an arrow that starts from 0 to 1 with an uncertainty circle being about 0.2. So if we play with this uncertainty level, say, for example, that we want like 2 sigma, which corresponds to 95, you see this circle getting doubled. If you save this script again and then run the same thing, you see that this is getting twice of the size. If you want 3 sigma, which is 99%, and do it again, see it's getting like tripled. So the next one we're going to play with is the correlation between them. For example, we want this to have some correlation between these uncertainties. If we give it a number, for example, 0.5, that means these 2 errors are kind of associated with each other. The increase of the one may or may not necessarily result in the increase of the other one. And if you run this script again, you see that the uncertainty circle becomes an eclipse that sort of represents more realistic errors. And close this. Next, we will be playing with this arrow over here. For example, if you want to change the size of it, we're going to use the -A option to control it. For example, we want to give it 20 pixel and with the +E, which means at the end, and the A, which is a fancy arrow. And if you save this and run this one more time, oh, you see that the arrow is becoming larger than before. Actually, there are more that you can play with. For example, we want at the beginning to be an arrow tail, then you just plus BI. You see now there's a tail over there. Yeah, 20 pixel might be too big. Let's change it back to 10. And for example, I want the arrow to be filled with, for example, blue color. Then you give it a +G, blue. If you save this and run it one more time, you see that it's the arrow and the tail are being filled with the blue color. And also the -W is actually controlling the line plot over here. But for example, if I don't want the arrow to be very thick, you can actually re-specify the width of that using the +P, which is giving it a pin, similar as the -W option, but for the arrow plot, let's give it a 0.1 pixel. And if we run it one more time, you'll see that the outline of these arrows are becoming thinner than before. And there's another option that allows you to plot only, for example, half of this arrow, which is +L +R. If you give it +L, save it, and run the script, and you see that only half of it is getting plotted. There's another thing that you can play with. For example, if you want to plot a right lateral symbol, what you can do is, for example, we don't want to plot any uncertainty associated with it. So we're just going to put 0 over here. And you run this. Oh, we don't want the tail either. Let's remove the +BI. We run it, and then this is half of the right lateral motion, right? And you can basically duplicate this line, and we want to plot the right-hand side. But we want it to be shifted a little bit so that the 2 arrows are not at the same place. So we're going to use the -Y shift option. Let's move it by maybe 0.2. But also to realize is that you don't want the arrow to be on the same side. So instead of EA, you want to BA. And if you do the script again, oops, I shouldn't have specified this twice. Let's remove the $JBR, and run this one more time. Okay, now you have a right lateral motion symbol. So that's pretty much for the vector attributes. Next, we're going to go through another example that's associated with the Ridgecrest, the 2019 Ridgecrest earthquakes. So let's start a new script. Let's call it GMT minus new script equals bash into plot map.sh. Let's open that right here. And we don't need this anymore. So let's call this, do the same thing here. We want to call it a figure name. Let's say it's called demo. And it's also going to be PNG. But before we really get started to plot this map, let's go through some of the files over here. So what's originally in the tarball is actually needs a couple of script. There's a couple of files. We can actually do a ls -l ht, and we should be able to see everything in that directory. So this dm.cbt is just a color table for plotting topography. And this GPS data are actually acquired coseismic deformation in it for the Ridgecrest earthquakes. If you do
Apologies, let me fix this again. I'm just going to stop and then restart.
head gps.dat is going to show you the top of few lines in it. You see it's composed of longitude, latitude, and east-north deformation. They are in millimeters, and also the associated uncertainty and their correlation. I mean, the last three columns are just made up, so they don't really mean anything over here. And this dm.dsam.grd is just a EM data over the region. You could essentially use the DM directly from the Hawaii website, but this one is a little bit different. This is the DM above the ellipsoid. I guess the one distributed at Hawaii is above geoid. There are some differences between them, but you could use either of them. This new files.gmt are actually the mapped rupture and the secondary ruptures, like cracks near the rupture from this event. And this de.grd and dn.grd are the deformation grids in the east and north directions derived from a kinematic slip model that's inverted from geodetic data like INSAR and GNSS. So after we have gone through that, let's start plotting. Again, we're going to make some parameters. Say that we want to set up some variables. The DM is actually this file, which is dsam.grd. And we also want the GPS data to be defined. So it's the gps.dat file.
Okay, apologies again. Let me try one more time. Okay, is it better? Is the screen better now? It looks so on my side.
Yes, much better.
Okay. Okay.
We also want to set the range, but over here, we're going to set the range based on getting the information from this grid file. There's a really useful command in GMT called GRD info, right? So if we run GMT Jrd info on this de.grd, you will see that all the information associated is getting popped out, right? You have the range of this and the increment, how many columns, how many rows, and the basic scale of this grid. So what you can do is that you can append some input with this command that's -i minus. This is going to give you the range of this grid. This is this x min, x max, and y min, y max, because that's what we need for determining the region for plotting, right? And it's going to give you this -r with the 4 parameters. So we're going to use this as the input to define this variable. How we're going to do that. So basically, you give it the quote here, which is the on your keyboard is the button that's left to your number 1 on top. You're going to quote it and then give it this command. So what this line does is that it's going to get the output from this command and assign it to this RR variable. So next, we're going to do the output. We already specified here, but we're going to define it again. Let's say we're going to call it demo and format being PNG. So here we can change this to $output and then here $format. So a good way of doing it, like setting a lot of variables at the beginning of this plotting script, is that later on you could just change any of them and then you can run this script again to create a map for other data. So let's start with plotting a base map. So it's GMT base map. And we're going to use the Mactar projection. Let's give it a size of 6. And we already have this RR variable, so we're just going to call it $RR. Again, we're going to set the -b option. Let's try A1F15. This time we don't want to plot the grid because in the map there will be other data like DM. If we save it and then run the slash plot map.sh, and it's going to give us a plot. Let's open it. Yeah, demo.png. A double column. Okay, now we have a map plot on the right. It's basically just nothing there, as it's just a base map. So the next, we're going to plot the DM data. So the command we'll be using is called GRD image, as we learned yesterday, GMT Jrd image. And the file, input file will be the $DEM, which is this DEM dstamp.grd. And we're going to illuminate the DEM with -i. And then we're going to give it a color table called dem.cpt, right? We have that in the directory. But if we run this, yeah, it doesn't look very good. The main reason is because this is too saturated. I mean, you do want snow, but you don't expect this much snow. It looks like Ice Age. So the tool we're going to play with over here is called make CPT. So we're going to make a new color table based on the color table that we have in this directory. Let's do it over here. GMT make CPT. The color table we'll be using will be the dem.cpt in this directory. And we give it a -t, which specifies for the range. You want to scale it. Over here, we're going to do a 0 to, I mean, the zeros are probably somewhere around a couple thousand meters. So let's try 3,000 meters with an increment of 200 meters. Then -d, which means continuous color table and also saturated at maximum number. So in other words, anything that's above this 3,000 will be plotted as a value 3,000. So let's call it dem2.cpt or maybe dem10.cpt. Then over here, we'll change this dm.cpt to the one that's just made. And if we save this and make the new plot, oh, it looks better. But somehow it feels like this gradient's a little bit too strong over here. So we're gonna tweak with this -I option with plus n to sort of tune the strengths of the gradient. We're gonna use a linear case. Let's try exponential this time, -e plus ne dot 3. If we save this and run the plot map, okay, things are less shaded and looks more reasonable, maybe. Okay, next we're gonna plot the coastlines just as we learned yesterday. Let me move this upward a little bit. So let's try GMT coast. We want to plot the boulders. We want to plot all the boulders, including the state boulders between California and Nevada. We want it to be, let's say, 0.5 pixel with black color and these dashed lines. And we also want to fill the ocean. There are like a tiny bit of ocean over here as well. And we're going to use the -S option with the ocean color, blue, light blue. And we want to plot it at full definition. And also we want the coastline to be plotted with some like maybe black line. So we can use the -W option with 1 pixel. Black. All right, let's run this one more time and see what happens. Save this first and then run it again. Oh yeah, like 1 pixel might be too thick. You can't even see this lake over here. Let's try 0.5, maybe 0.1. Save it. Now we can see the lake. Cool. After that, we'll be using the command called GRD vector to plot the vector deformation field. So over here, and we're going to plot it on top of this whole thing. GMT GRD vector. Let's give the input file called de.grd and dn.grd. Over here, there will be a -S option to sort of tell you the scale that's going to get used. Over here, we're going to give it like 50. Because if you think about the deformation we just saw, actually the range is like largely from -100 to 100. And since we're using the 6 as a size, we want the largest vector probably being like somewhere less than 2. So we're giving it this 50 over here. And we want the -I option, which is just 0.1 increment. So every 0.1 degree is going to give it new input vector. And the width to be, we want it to be very thin because we'll be plotting a lot of vectors, 0.1 pixel. And for the vector attributes of GRD vector, you'll be using the -Q option. Or here, we're going to give it a 10 pixel size at the end with a, we're just going to do a plain error this time. Oh, it's plus EA. Right. And if we save this and run it one more time, yeah, it says no unit specified in -S, but it's okay. Now you have this vectors plotted, like you can sort of see this lateral motion, like the rupture this way and that way. Also in this GRD vector command, there is this new auto labeling option, which is called -L. And for example, I want to give it, because the scaling that you're giving here is about 50. I'm going to try this default 50 millimeter. And if you run this one more time, you have this automatic label on top. But if you want to plot, for example, much smaller like label, I don't want this to be 50, I want this to be 20 or 30 maybe, you can actually change it over here, but you also need to give it a +S option to scale this, because that's basically only like 0.6 of the 50 millimeter. So you're going to use a 0.6 over here. If you save it and then do it one more time, then this auto label becomes 30 millimeter. Okay, what's next? Next, we're going to plot the faults on top of this. And the command we'll be using is called GMT plot. The file is new faults.gmt. But before we do this, let's take a look inside what's in this data. And you'll find that this is basically like a bunch of segments that records where the rupture starts and ends and how it occurs in space. They are separated with this -L in the data. So GMT knows like there are like multiple segments that you'll be plotting. And we want it to be, for example, 0.5 pixel wide with, I don't know, maybe orange colors. And we save this and run this dash plot again. Oh, you see some like new fault ruptures in it. All right, next we'll be plotting the GNSS data. But before we really do that, we want to plot the GNSS stations first. We're going to use this plot command again, and then $GPS. We're going to plot them in triangles with maybe 0.15 sides. And the outline will be in 0.1 pixel with black colors. And for the fill, we're going to give it maybe in green. GREN. Then we save this and run it. Okay, all the GNSS stations shows up on this map. Next, we're going to plot the vectors, GMT below and $GPS. We're going to use the same scale that's specified here, -S, because this is the length scale. Let me try to put an L over here so that it doesn't warn me anymore. -S 0.02, and we want to plot because uncertainty with Azan it's pretty small. Let's do a 9.9 so that you guys can see the circles, and font size being 10. And we're going to use the -A option, 10 pixel size arrowhead at the end with a fancy arrow, and then we're going to give it a width of 0.1 pixel, and I'm going to use blue colors maybe. And for the fill, we want to give it the black colors. And if we save this and I'll recognize, oh, I forgot to give it the -SE. Do this one more time. Ooh, what happened? Yeah, I don't know what happened, but oh yeah, it's just -L. Leave that for the moment. Essentially, you could do the same thing at this scale over here, which is -I.02. So they are the same. Now that we have finished plotting all the vectors, but what if we want to plot something else? For example, we want to plot the amplitude of the deformation on top of this map. While the deformation is being shaded with the topographic information over here, and then you use these vectors to denote the deformation direction. So how are we going to do that? So the way you do it is actually, you could create a new grid using the GMT functions over here. For example, so GMT is actually a pretty powerful tool that can not only just do plotting, but they can calculate the grids as well. So the command we'll be using is called Gmt Jrd map. So the way we do it that because we have the eastward deformation, north deformation, we can combine these two together to get the amplitude of deformation. And this GRD mass also uses a format called the reverse polish like approach or something. You guys can Google that. It's a pretty fun way of writing things. So we're going to give this DE.jrd, DE.jrd. We're going to multiply these two together. We're going to do the same thing for the north component. And then after these two squares of E and N, we're going to add them together and then do a square root of it. And the output file, we're going to just call it like D.jrd or something. So now we have this amplitude image. Let me make this a little bit wider. So now we have this deformation grid. Then how are we going to plot it? We're going to need a new color table, right? So we'll be making a new color table. We'll be using, for example, jet. This time we're going to do a sort of red to green. We're just going to use half of the color bar. So we'll be using -T option from negative. We want it to be a little bit saturated so that you can start to see the impact of the earthquake. Let's try 30, -30, 230 with a 5 increment -C into D.cpt. All right, but we do want to plot this before we do any other overlays like the coastline and the vectors. We want it to be on the background, so we had to select the position to implement it. So we're going to replace this GRD image command of the DEM with the deformation. So we're going to hashtag this to comment it out, and GMT Jrd image D.jrd -C. We're going to use the D.cpt file. What else? I think that's pretty much it. And if we save it and run this one more time, oh, you'll see that they have the deformation field in the background, right? Okay, next we're going to shade this image so that we can see some of topographic information. And the command we'll be using is called Gmt Jrd Gradient. This is similar as the -I option where you are plotting using the GRD image, but this is more flexible that you can use a lot of parameters to control it. But before we do that, since we're going to use the shading of this deformation grid, you have to sample your topography grid to the deformation grid first, so that those two grids are matching up. So we'll be doing a GMT Jrd sample, the $DEM and -R DE.jrd. So this is actually sampling the DEM to the size and sampling of this DE grid. And output grid will be, let's call it a DEM temp.jrd. Now we have this DEM temp. We're going to work the gradient on it. Again, we're going to use the -N option to specify the, how to say, which direction you are essentially, not which direction, like how large of a gradient you're going to give it. For the moment, let's try the NE.3. And you also need the -A option, which is like which direction you'll be doing this gradient. The default is -45, so we're going to just use -45 degrees for the moment. And the output grid will be DEM temp gradient of GRD. If you save this, and then while you are plotting this GRD image, you give it a -I option, and then give it this file name. So it's going to use this file as an illumination for the plotting. if you save this and run it one more time, now you can see that the the topography information are actually shading the image, which is pretty cool. Okay, I think that's pretty much everything for plotting vectors. If you go to that GitHub page that we started, you see that there are more things that you can add to this map, like the focal mechanism, the epicenters, and maybe you can find like data for other earthquakes to play with. So feel free to experiment on that. And I think I only missed one thing from this plot web, which is how do you like color these vectors? So I'm gonna try that and sort of like show you guys how to do it on this plot web script again. Let's try to open that PNG file, do a double colon. So actually, GMT allows you to sort of build a color table to color these vectors. I didn't like sort of go through that at the beginning because that's sort of like a new feature I think Paul just implemented. And we're going to expand the data a little bit. Let's try it without this double couple. Let's comment it out. And we don't want just half of it. And duplicate these lines like 3 times so that we have 3 vectors to play with. Now let's change this start and end. Let's start from 0.5 for this one, and also we want the deformation to be 0.5 and 0.5. Then we get a slightly smaller uncertainty. The other one, we're going to start from -0.5 and with large amplitude. So you see like 3 vectors in this plot. Give the larger uncertainty. Let's just give it some strange numbers. Let's do this. Dash plot web.sh. Oh yeah, forgot to comment this line. And you also need this part to be double redirect because that's like creating a file and this is appending to that file. So you have 3 like lines of data in the file. We run that one more time, you see like 3 vectors parallel to each other. We do want the error bars to show up. Give it a 0.99. Oh, that's too big. This file is good. All right. So how are we gonna color these? Like, if you want to give it a color table, you can actually, but you need to make a new color table first. Let's do the GMT make CPT one more time. Gonna use rainbow with -T0 to 2.5 and like 0.5 maybe. B minus T into web.cpt. Then what you can do is that you sort of give this a -C option with the web.cpt. If you save this script, run this one more time, give it, seems nothing's getting changed. But that's because you have this +G option that's overriding this coloring option. So we have to remove this part in order to let it work. Run it one more time, you see that these arrows are having different colors now. And we're gonna make a color bar over here, GMT color bar -C web.cpt and to -dx. And start with 0.1, 0.1 plus W is to 1.5 over 0.1. And save it. Now you have a color bar that tells you like how large are their values. And the thing is that if you want to, for example, not just color the arrow, but on the other hand, you want to color these lines as well, then you have to modify this -W option. You have to give it a +C. Then it's going to color the lines as well. It's using this curve table. If we save it here and then run the bash again, they're going to be with these colors. Another thing you can do is that if you're really bothered by this outline, you don't want it to have a black outline or any color outline, you can essentially just give it a 0. Or no, you can just essentially give it a no input over here, so it's not going to plot anything. Now things are becoming a pure color. Okay, that's pretty much everything I want to show here. Feel free to play with the data. Thanks.
All right, we should be back. Can you all see my slides?
Yes,
I can.
One can and all can. Excellent. All right, so the last section today is going to be about making animations with GMT. And because we only have time for a little bit playing around, you could look on our website for more examples and go to the YouTube channel, which you can get to from the main GMT site for longer animations. So in GMT, to make movie, we need to make use of two modules called movie and events. So basically, making movies is simply creating a bunch of same size frames of PNGs or JPEGs or whatever, and put them together in the right order and play them back in a reasonable time. So there's sort of two time axes here. One is the playback time, how many frames per second do you want to use? And Hollywood movies are 24 frames per second. You may slow that down. And then we have the animation time, which is what is the time in real time between each frame, because they could be nanoseconds or millions of years, depending on what you do. So, but we want the time constant between two frames to be equal, otherwise it gets sort of out of whack. So our trick here is to select these playbacks and animation times so that it properly represents the science you want to show. To make movies, it's no different than making GMT plots. By default, we have a canvas size that is sort of a typical page of paper, but depending on the specifics, it could be a 16:9 HD kind of format, and then the paper size is a little bit different by default. You can change these things, but that's the default. And if it's more 4:3, then it's different dimensions. But basically, you compose your plot as if you were making a real figure, and you move around on that page with -X and -Y. So there's a couple of quotes related to repetition here. You all heard about Einstein, who said that insanity is doing the same thing over and over again and expecting different results. This is one definition of insanity. And I have another one here, that GMT animation is doing the same thing over and over again, but getting different results. So how can we do that? Well, that's the whole thing about variables. We're going to write a script that is the same thing, but it's going to actually produce different things through the use of variables. So we will see that when we write a GMT plot movie script, that it looks like a GMT regular script, like you've been doing the last 2 days, but then we're going to change something about the script that we want to vary between the frames. Otherwise, we get the same frame again and again, the first case with Einstein. So we want to change things. And we'll see the special variables that get assigned for us that we can use in these scripts. Often we have movies that have a constant background image, like a topography image or something. We can specify we want a certain thing to happen in the background, or alternatively, a certain thing should be laid on top of all the frames. So those are only done once, and they can even be a finished PostScript plot. And then movie takes care of everything else, and it will use all the cores in your computer and run all the frames and put them together into a movie. So here are the special variables that are created for you. And they have names like movie width, movie height, movie dot per unit, rate and end frames. If you need those numbers in your script, they are available to you. But here's the more interesting things. So these are variables that change for each frame being computed. All right, so let's say we have a data table that has hundreds of records, and the 48th record looks like this: 56 west, 23 north, 45 minus 3,500, x5 Atlantis. That's one record in the data table. Now, if you want to use some of those numbers in a script for that particular record or frame, we would use these various variables on the left here. So for instance, $frame will have the current frame number. More interestingly, movie column and then a number will have the value at that record for that column. So say movie column 3, when we're doing the 48th frame, it will be minus 3,500. That is the third, counting from 0, 0, 1, 2, 3. Basically the fourth, in a sense, column in that data record. That will be minus 3,500 when we run the script and that particular frame is made. If you have trailing text in your input file, like here, X5 Atlantis, you could use movie text, which will be the whole sentence, X5 Atlantis, or you could specify a word of the text with movie word 2 or movie word 1 and so on. So we're going to do a very simple example to see how this actually works. We're going to make a movie of the Earth spinning around using the orthographic projection, and we're going to use the central longitude. That's going to be the frame number. So as the frame number goes along, we're going to basically pick a different viewing point for this projection, and then we'll put these frames together, and we will see that the Earth is spinning around. And we'll do this at a pretty low resolution movie format, like 360p, since we don't want to wait for everybody's computer to do all the higher resolutions. So, and then we're going to play with this a little bit. So I'm going to stop the this presentation here. Hold a second here. I'm going to stop the share. It won't do that. I'm going to start the share again. There's my code. Share. All right. So I'm going to start a new script. I'm going to call it globe.sh. And it's going to be a GMT plot that we've done before, GMT begin. I'm going to call it map. And I'm going to do a coast job, GMT coast. I'm going to make a... Yeah.
Paul, we are not seeing your screen, only you.
Although I shared it, you're not seeing it.
I'm not seeing it.
I can see it.
I could see it.
I could see it.
Oh,
Okay, Joachim.
okay, so forget, I can't still, but no problem.
I'll share the desktop. Maybe this will... Is that better?
No, because I was seeing it before you interrupt, but okay, continue. Maybe something with iPad.
Yeah, okay, so the rest of you can see it, right? When I type here. Okay.
Yeah, if the others can see it, okay.
Yeah, that's more important. Okay, I'm going to make a global map. So G for a global map. I'm going to use the orthographic projection, which takes a central longitude. I'll do 30. A latitude. I'll do latitude 30. And I'm going to do a 12 centimeter plot. I'm going to give colors. So, okay, I'm going to do burley wood, which is a pearl color, for land. And I'm going to paint the ocean tomato color, horrible color. If you don't like my colors, you can change them, right? These are my colors. I get to choose. And I'm going to draw the grid lines. And I'm going to, well, let's do that for now. And that's it. GMT end show. Save that. And in the terminal, I'm going to run bash globe.sh. Second type. Fantastic. Okay, a map from space. basically orthographic projection. The colors are horrible, but if you don't like them, you change them, right? Okay, so now I want to make a movie where this thing is spinning around. Well, what's going to make it spin around? Well, it's going to be this number here, right? The central longitude. If I change that to 80 and run it again, I get the view from longitude 80. Great. So all I need to do is to have this number change in a sensible automatic way. And the way we're going to do this is to use these variables. So since we know that the frame number goes from 0, 1, 2, 3, 4, so on, I'm going to use that variable as my longitude. All right, so I'm going to say, change this 80 to $movie frame, whatever that is. And that's going to be my central longitude. Well, it's not going to happen by itself. The movie command has to do this. So to keep things simple, I'm going to write as a comment the movie command inside this script. So it's just a comment. And it's going to be GMT movie. And GMT movie is unusual in that its input is actually a script. In fact, it is this script, globe.sh. And I'm going to make a movie, pretty low resolution, 360p, so 360 lines. And it's an old 4:3 format, I think. I'm going to have the longitude swing from 0 to 90 inclusive. So that is 91 frames, 0, 1, 2, all the way up to 90. And I'm going to call the product globe. It's going to be a name of the movie and the other product. And before I make a movie that might take a long time to run and realize that I screwed up, I'm just going to make one frame to look at it. So I'm going to pick frame 55 and PNG. So that's what I want to run. Okay, so I've saved this script. If I run it, I'm going to just get an error because GMT movie frame doesn't exist, right? But I'm going to copy this command here, copy it, and place it in the terminal and run it. And I got nothing up here. That's very strange. Why did that not happen? Sorry about that. Couldn't I run this before? Globe. Okay, something weird happened there. All right, I got my globe. All right, so I know that the script sort of works, but I'm going to position the plot in the center of my paper. But the paper here is whatever the dimension of this 360 layout's going to be. So if I run this again, this is my computer not liking to open things. Sorry about that. All right, I get something like that. So if you try the same script that I did, you should get something like this. This is one frame in a movie. This is frame 55, counting at 0, in the movie I'm going to make. So now I think we can try to make the movie. I'm going to copy, oops, this comments. Remember, these are just comments that I place inside the main script that actually is driving the movie. So now instead of making just the 55th plot, I'm going to make an MP4 movie. All right. So this should now run this script here 91 times. Oops, what happened here? There we go. Sorry, I'm not happy about this VCS MP4. This should now run this script 91 times, create 91 PNGs, assemble them into an MP4 movie. And this will take a few seconds to run all those jobs. Okay, it's done. So it can't be shown in that editor, but I can open it with open globe.mp4. And there's my little movie playing. Can you see the movie?
Yes, I can.
Yeah, okay, very good. All right, so that was pretty easy. Made a little movie there. And all I did was to write, I started with a simple GMT script, thinking of a piece of paper, and I picked a particular longitude to just sort of make that plot. And then once I had a plot that looked sort of what I wanted, I said, okay, this particular part of the plot, which specifies the central longitude, I want to make that a function of time. So I replaced it with, in this case, movie frame, and let movie take this plot, this script, and run it automatically in the background for all these different frames, and then assemble all the frames together to a single movie. If you look in your directory, if you run this thing, there will be a directory called globe, and it has all these 91 figures, right? Because I didn't say delete them when you're done, because maybe something went wrong with making the movie. I don't want to redo the whole work. So it is still there. We're gonna try another little wrinkle here. There's my movie script. We want to have some sense of progress. So there's different progress bars in GMT. You can numbering the frames. You can number the elapsed time. You can have a little indicator that shows how much of the movie has progressed. And I'm going to put on PA, which is one of 6, I believe, indicators of progress. So I'm going to do this. I'm going to do 2 things. I'm going to add a -z option. And what that does when I run this command is to delete the directory with the temporary PNG files, because otherwise it will refuse to overwrite them. So I'm going to remove the one I had, which is globe, just so that it is gone. And then when I copy and paste this command with the Z, I added the PA. It's going to add a progress indicator. And if I play the movie now, you'll see up in the top right corner, there's a little indicator that shows, how long the movie has played. Pretty simple. There's 6 of these things, and you can position them just like you do a color bar, one of those 9 special points on the paper with the justification. And you can, of course, you could change colors and sizes and all that stuff. But that's a straightforward one. We can also add a frame label, frame number, with the -L option. The L option can be complicated. You may want to do setting actual time, month, day, year, that sort of thing, clocks, or just a simple frame counter. I'm going to do the simple frame counter here. And I'll run that. All right, movie's done. And now we should have a little frame counter up in the top left corner. 19. All right. So that's pretty simple. You can have these are built into the movie program with a couple of options, so you can easily have it do that for you. The cool thing about these options is that right now, I should back up. So right now I was just using the movie frame because that was very convenient. I'm just going to do 1 degree change in longitude per frame. And movie frame is an integer, obviously, so I can only do 1 degree at the time here. But what if I wanted a movie that moved 0.2 degrees between frames? Then I couldn't use movie frame. Then I would have to use those other special variables called movie column 1, movie column 2, and so on. So we're gonna do, let's see here. Before I go too far here. No, I think we'll stop there. We can play with this more later. I just wanted to show you how that works. So before I go further here, is there any questions about what you just saw? I try to keep it as simple as I can with a single GMT command here, Coast. But I hope you get the question here. The key thing here is that you have to use some variables that have to change between each call. And they can either be from a table or they can be just from the frame counter. So before we're going to do breakout and stuff, I'll want to talk about symbols. So you've seen.
I have one question.
Yeah.
Very good. I got the MP4 video, but I have the question about the quality. Is there any option that we can increase the quality for the videos that we create by GMT?
Absolutely. So right now I did 360p because, you know, we're live and we don't have much time. So this is pretty quick. But I could do a 4K movie and we'll sit there for 5 minutes and it'll be a beautiful 4K movie that's, you know, that's actually the resolution of my laptop. But
great. Okay, by that option we can check it. Yes.
Yeah. So the higher resolution you have, the longer it takes to build each frame. It sort of scales almost linearly. And the longer the movie is, of course, the more frames you got, then the longer it takes. So I've run movies like the ones I just showed you that took what 5, 6 seconds to finish. And I also run movies that take in a couple of hours or overnight. So it's all in how many frames. So yeah, that's a good question.
Very good. Yes, that's interesting. Thanks a lot.
All right, I'm going to talk about points versus events. So you've seen throughout the last 2 days, you can plot circles and lines and various symbols on plots with, you know, GMT plot, for instance. And you can plot fancier symbols like beach balls with mecha and vectors with velo and so on. That's very nice. But in a movie context, what do we want to plot? Let's say we want to do seismicity. If you're going to make a movie of seismicity, you don't want to plot all the seismicity at once. That wouldn't be a very interesting movie. So clearly you want to plot things as they happen, I guess. So if you want to make a movie of, you know, all the seismicity since 1960, in the beginning, you presumably just plot the first quakes in 1960, and then as the frame goes forward, the frame may represent some fixed time increment, like a day or a month or 2 seconds or whatever. And then you're going to keep plotting things that have happened in that little interval. And then, of course, your screen going to get clogged after a while with all those quakes. So maybe you want some of the quakes that have been on for a while to sort of fade away, to not dominate the plot. So that gets kind of tricky in a scripting sense. You know, how do you plot just a portion of it as time changes? So we realized that we needed a new tool for this, and that's how Events was born. It's a tool that only plots the data that should be visible on any given frame. So you can think of it as a hypercharged plot command that plots things, but it's sort of restrictive. And it can even plot these symbols from Mecha and Coop and Velo as well. So just scroll this manually forward. The way it works is that you can imagine each event that you want to plot. Let's stick with the seismicity because it's sort of easy to understand what an event is there. A quake happens. So prior to the quake happening, the quake should not be plotted, right? It hasn't happened yet. So the green line here is flatlined at 0. Symbol size is 0 until the beginning of the event right here. Then the symbol size should be 1 times whatever symbol size you want. And then it stays for all the frames that follow, perhaps until some time you decide, well, I don't want to see that quake anymore, and it goes back to 0 again. So that green step function here, you can imagine 1 being attached to every single data point as they slide, you know, in different time direction. So you can do that, but you can also spiff it up a little bit by having the symbol size change, like the black line here, a little bit before the event. So it sort of builds up to a large symbol size and then decay down to sort of announce that, wow, we have a new event. And then maybe it will decay back, not to 0, but some smaller size in the end. So we can control the size of symbols through time You can also use the same thing with similar curves to control the color intensity and even the transparency and even the color. So you can make something very complicated by associating each event with some event curve like this. So we're going to demonstrate this in a relatively simple example, which is the Pacific seismicity for 2021. So for you to do this, you'll need to, okay, so for each frame here, we're going to specify central longitude. We're going to plot the background coastlines, and then we're going to plot all the events that should be on that time frame. And if that works, we could make it fancy by using a GRD image topography background or something. But the first thing is that you need some data for this to work. We're going to get it from USGS, and on the GitHub page, you'll find a script which you already have downloaded, presumably when you cloned it, called get quakes. And I want you to run get quakes in your terminal here. So I have get quakes too, right there. We're not going to, I commented so you can read it, but basically it's a script that will go to the website and download data and scale it for us without us having to click on web pages, right? Because you may not be there. You just want to run this thing once in a while and make a movie. So I'm going to run getquakes.sh. And it does a couple of things. It creates a data set of all the quakes that happen in 2021, 5 and larger. And it scales the magnitude by 50 to simulate a certain diameter of a symbol on the Earth in kilometers. So that's quakes.txt. I'm also creating a standard red, green, blue seismicity color table. So shallow quakes 0 to 70 kilometers can be red, 70 to 300 are going to be green, and deeper than 300, 10,000, which is deeper than the Earth, can be blue. And then I'm using GMT math down here to create a data table of longitudes. So basically, I'm going from, I think I'm going from 200 to 240 in longitude over the time period of that 1 year in steps of 1 day at a time. And that's the times.txt file. So with those little bits, I'm ready to try to make my Earth movie. And in the interest of time, I think I have one here. No, that's not the one. Where's my other one? Quakes.sh. So I'm doing exactly the same thing that I did for the globe. I'm writing a little GMT script that you can see here. All right, the GMT begin, GMT end show. It has a coast. And the coast just looks like the same movie before. Here's the globe, right? It's a coast command, colors, -J, -R. Same thing, -R, -J, G. But now I'm using movie column 1. And movie column 1 is going to be the second column in my data file times.txt that I made. So times.txt looks like this. It was created by the script. It has dates there every day. And then it has a longitude that goes from 160 to 200, I think, to 240 linearly. That's my script. So that's going to be the same kind of map you just saw. But then I'm going to run GMT events. That's going to plot the earthquakes with colors given by the CPT. I'm going to plot them on the 3D surface of the Earth as ellipses of a certain dimension given by the magnitude. And then I am attaching these curves to each event to scale the size and the transparency and intensity of the color. So it will take me a little bit too long, I think, to explain the parameters. These are, specified in the man page for, how long the event should be up before it sort of fades back down. How big should the initial symbol look like? And what's the change in color over time, and so on. So that's what these options to events does. And then I have, again, commented out a whole bunch of examples here. So I'm going to try one of these, and you can try with me if you have the you have the access to the files there. You save the typing for now. I'm going to copy the first one here, which going to just make no movie. It's going to make a plot of one frame. It's going to be frame number 50. So if all have gone well with the getting the data, this should run. And it did. So this is one frame in the movie at frame 55. That happens to be February 20th of last year. And at that particular day, you can see 1, 2, 3, 5, 6 large symbols. These are quakes that are just happening around this time. So they're sort of blowing up in your face. And then quakes that have happened just a few days earlier have sort of subsided back down to an intermediate size. And then quakes that happen in January, they're just dark and very small in the background. So this worked well. So what I would do if I compose this kind of movie, I would make just a plot like this, just one particular PDF frame, PDF because it's higher resolution, and tinker with my parameters here in -e and -m until it looks about right. Well, then I will do the same thing, but with a PNG frame, because I'm still doing 360. So we'll just see how rotten it look at that small. Oh, and the Mac doesn't like to open something automatically, does it? Now it's okay. Sorry, open quakes.png. All right. I have to fight my Mac here for a second. It's very irritating. Force quit preview. Yes, I want to force quit preview. Open quakes. There it is. Okay, so that's one frame in my movie. It's okay. It's small, but you know, it's quick. So now I can run the same movie, but I do not need to see that frame anymore. I'll take out the -m option. And instead of none, which is not needed, I'm going to say MP4. So that means make MP4 movie. LC0 means label the 0th column in the data, which is the time, and turn off the clock, just do the date. All right, I'll run that. Again, look at the plot here. It's just 2 lines, right? Lay down the coastline and then plot stuff on top. The rest is all happening by the movie program, who is, you know, doing these. How many are there? 100 frames. There's done. Okay. So now I can open quakes.mp4. And it's a small movie. Starts on January 1st. And I can play it. And you can see what I mean by popping up and showing that the earthquake arrived, and then they sort of decay back into a background. And these are all the quakes that happened last year, but we only see it from the Pacific side, right? So it's going to go to the New Year's Eve, and there was a big quake up in Alaska, and one near the North Pole, apparently. That's interesting, right? So, and you can see the date comes up in the top left corner here, because I didn't plot the clock. Could plot the clock also, or just the clock, depending on what we're doing here. But that's where we are. So we only have a few more minutes here. So I think we have, no, that's not right. We have, what, half an hour? Is that right? On my clock? My clock is coming up on 8. So I think we have plenty of time for breakouts. Let's see if I covered everything I want to cover. Yes, I did. So in the breakout rooms, I think you can do the following things. You can play with either one of these 2 scripts. For instance, you can do the first one and just try to increase the resolution. So let's say if I go back to my globe here and I say, well, That was very nice, but it was really crummy resolution. How about, I'm HD already set there. I'm gonna make an HD movie. All right, how long did that take? 5 seconds, 10 seconds. Oh, it's done. Okay, open Globe MP4. Right, now we're talking. Look at those beautiful tomato colors in the ocean, right? So here we go. So now it's HD, 1080, 1920 by 1080, right? That didn't take too long because the plot is super simple. I could do the same thing with my quakes, but that's, how many frames do I have here? Got to count times .txt. 365. Oh, duh, it was one per day, wasn't it? So 365 frames. Yeah, so maybe it'll take 3-4 times as long. But you can play with this. So you can see the -C option here controls what's the resolution of the plot. How do we know what's available? GMT docs movie, -C, canvas. All right. Here's preset formats. You know, you can do 8K. If you have a way to display 8K, you can, doesn't matter. 4K, ultra high definition, or HD, 1080p equivalent, and then it goes down. And then similar things for, you know, XGA and SVGA and DVD formats down here. But you can also do a custom one. So if you want to make a plot that is, you know, 3 inches by 3 inches, a square thing at 200 dots per inch, you can specify that as well by width X, height X, dots per unit. So you can make your custom funny portrait film if you want, which is maybe handy for, you know, a PowerPoint presentation where you don't really want the whole screen because you're just showing a portion of it, and maybe you're showing something that works better in portrait. You make a portrait movie. Go back to my slides here to see if I, oh boy, there. Right, so, okay, I'll go back to my scripts actually, so talking from the script. So you can either play with the first one and change the colors and change, you know, the type of plot, the size of things, maybe put 2 spinning Earths in there if you want to be sort of risque. Or you can play with the earthquake data set and change some of these parameters here. What happened if you change this 5 to 2? You know, that's going to change the initial burst of activity, how small or big they are. This coda here, that says after the quake is sort of done its thing, shrink it down to half its size. That's what the coda does here. You can change that number. This one here for MI is the color intensity. It doesn't change anything. It's at 1, but during coda, after we sort of turn it off, it changes the color intensity down to -0.6. That's going to darken things. It's like being in the shade, and so on. So you can play with these parameters and you can change the resolutions. And I think that's a good sort of way to get a feel for how movie making does. Because if you change this thing too much, you're making don't make a 4K movie during this breakout room. It will take too long. But you can probably, depending on the computer, I mean, you saw mine did the HD in just 10-15 seconds. Depends on your computer. I happen to have 20 cores. You know, so that means 20 jobs are running simultaneously, making 20 frames at a time. It goes quicker that way, right? And it's all assembled at the end. All right, so I think we should do the breakout rooms now. I'm going to stop my share. We should do the breakout rooms, and it's sort of anything goes in the breakout rooms. You can start with those examples and explore some of the parameters to see how it affects your movie. And if you're excited about making movies, you can start thinking overnight and you sleep. What kind of movie would be cool to display the science you're doing? Because maybe you pick that as a project instead of a static figure for a paper. Well, I had fun. I don't know what you guys did in the other rooms. I had fun messing around with movies. So it's the end of the day. We are sort of gone through all the things we wanted to show you over these 2 days. And tomorrow we're going to put that to good use in making your projects. So you can spend the night thinking about what your project will be. The bare minimum, I would say, is a sort of professional looking figure 1 in a thesis that shows your data and what you're trying to accomplish with the tools you've seen. It shouldn't be a copy and paste of anything we did directly. We will expect more of you, but you should be able to do something nice. And of course, the whole point is that this is a figure that you actually will need to make for your paper or thesis or something. So this is going to help you to make that figure. So you should put some effort into this thing here. It doesn't have to be done by the end of the day. It can be a few days later, but it shouldn't be a month later. We're not going to wait around and grade things in a month from now. Or you can make a movie. I think that's also okay and acceptable. So you can dream about that tonight, and then when we meet tomorrow, we'll talk about the project and we will get you started, and then we'll be available for you. That's sort of the morning session, right? And then there's an optional afternoon session where we're going to demonstrate some of these wrappers. And I think plan is for me to demonstrate the oldest one, which is the MATLAB wrapper, which is getting a little dated now. I think it's only going to really do classic mode GMT, as far as I've been playing with, but we'll see. And then Joachim's going to do the Julia, and I think Mac's going to do the Pi GMT to give you a flavor for how those other environments can use GMT without leaving that environment. And I think that's all I got to say, right? Did I leave anything out? Max, Federico, Joachim, Eric?
Yep. Just so people are aware, we'll review the final submissions by creating a final products channel in Slack, and you'll put the output from your GMT script there. And if you do create a movie, we'll ask you just to output 1 frame rather than uploading the entire movie to Slack.
Yes, that's a good point. We don't want the 2 gigabyte long version clogging the Slack. Yeah, thanks for that. I forgot to say that. We'll repeat that tomorrow, I think, and make sure everybody knows what they're going to do and when they have to do it. All right, with that, I think it is bedtime, breakfast, lunch, dinner for everybody. And we'll see you same time tomorrow at 14:30 UTC, I believe. Take care.